and habilitation from the University of Jena. He had a long career, and he's the leader of a group on computational astrophysics. Mainly, his field is mainly directed to disks evolution and planetary formation. And also in his group, they work with SPH, so smooth particle hydrodynamics. And recently, from the last 3 years, we started a kind of collaboration between the two groups. So we send a few students there to spend some time internship in his group. And we brought one of his students to give a short course here about SPH to us. And so the collaboration is increasing, and it's a pleasure for us today to have Professor Kley here. And so at the moment, I think we have one student there. I think, no, I'm sure. Patricia is there.
Yep.
And perhaps in the near future, we are going to have somebody else going there from our group, and let's keep working together. I think we have a kind of complementary field of studies, and I believe we can increase this collaboration. So today, Professor Kley will give us a talk on dynamics of circumbinary disks and embedded planets. So Willie, if I can call you that, like that.
Yes.
The podium is yours, please.
Yeah, thank you, Otton. Thank you for this very nice introduction, and thank you, of course, for the invitation to come to you to Brazil and present this talk to you. I hope you will be able to see me well and to understand me well, and to see also the presentation which I'm planning to share now, which, let me see, okay. So it should come up, I think. Okay, you can see it, I hope. Yes,
yes,
this is
okay.
the title page. I will go into full screen mode and hope you can see that as well.
Yes, it's fine.
So yeah, thank you very much. The title, as mentioned already by you, is Dynamics of Circumbinary Disks. That will be the first part of the talk, and then I would like to discuss the evolution of planets that are embedded in those disks. And this is work done in collaboration with yes, my pointer is seen, with Nader Hagigipur. We started this some years ago. Then with Daniel Thun, whom Ricardo knows very well, and also Barbara, of course. And then recently, but now already since 2.5 years, I think at least 1.5 years at least, Anna Penslin, and she's a PhD student who is continuing that work here. So this is the organization of the talk. First, a little more general introduction to the field. Then I will talk about circumbinary planets, brief overview, then the disk dynamics, and then we'll add some planets to that, and we'll discuss the evolution of the combined disks and planets, and then a very brief summary. Yeah, there are sometimes pictures like this here on the side, the GG-TOR system, which is one of the most famous, I would say, circumbinary disks, because you can image it with several telescopes here in the infrared. Here you see here the big disks surrounding these binary star system, and the separation of the binaries, to give you a scale here, is something from 40 AU to 60 AU. Okay, that's the size, and the ring here has a size of 180 astronomical units. Okay, that's just a little teaser here. Binary stars. First of all, a little point here. They are abundant, of course, as you all know. And plotted here is from a paper from Rakehaven, 2011. The period distribution of binary stars, where they have a histogram here. The number of binary stars is plotted on the y-axis, and the period distribution here on the x-axis. And you can see there's a peak at around 300 years or something orbital period here, and about 1/3 of all systems are binary stars and binary stars. Okay, and the systems we are talking about today are here at the lower end of this distribution here. We will be talking about very compact binary stars that are surrounded by planets even. Yes, I mean, if you had a planet around stars in this binary stars in this regime here, obviously it would be very hard, if not, of course, impossible to detect them at all. Okay, so we are talking the lower end of the period distribution of all binary stars here. During the formation of a binary star system, the binary star is typically, as ordinary single stars also, surrounded by a disk that is a consequence of the angular momentum conservation during the initial cloud collapse that formed the star. And very interesting here is, or the specialty, if you have a binary star, is that the binary star exerts a torque on the surrounding disk due to its gravitational action. And so the binary transfers angular momentum from its orbit essentially to the disk, and the disk gains angular momentum and then will recede from the binary, and a cavity will form around the binary. Okay, there's an empty region here, which you can see here, for example, here, where there's no material surrounding the binary, and the mass is here a little bit outside. Okay, and this has as a consequence first a impact on the dynamical evolution of the binary itself. So the binary tends to shrink due to these gravitational torques exerted by itself onto the disk, because it gives angular momentum away to the disk, so it loses angular momentum. But at the same time, the binary star accretes angular momentum because there's still a mass flow from the outer disk here. You can see this here, these little streamers here. It's hard to see with the mouse here. Okay, the little streamers here. Through those streamers, there will be a transfer of mass onto the binary and angular momentum. And the question is, how does the binary evolve under the action of these processes? This problem has been analyzed very nicely a long time ago now. As you can see, 1994, last millennium. So by Pavel Atimovich and Steve Lubo doing SPH simulations. They have a theoretical part and they have an SPH part here. And this is a very famous diagram where they give the size of the inner cavity, which is on the y-axis here, as a function of the binary eccentricity here on the x-axis for different disk viscosities. And they are quoted here. These numbers you can see here is actually the Reynolds number. So this would be 3 would be 1000 and 12 would be 10 to the 12. So very, very high. And obviously the simulations can only go up to Reynolds numbers 10 to the 4 or something. Okay. And you can see that the cavity size increases rapidly with eccentricity of the binary, and the eccentricity here goes for the cavity size goes for very small binary eccentricities in these simulations and the analysis to 0. We will see how this holds up in our later studies here. Okay. So disk dynamics, after this early study by Pavel and Steve in 1994, has been studied then by Greg Loughlin, Michael Rosicka, and then by ourselves already. My very first diploma student in Tübingen, actually, Richard Günther, and myself, we worked on this those times. But then there was a little break, I think. There was not much further studies, dynamical studies here. And I may say that the first paper here is SPH, and the other two, Loughlin and our paper, is with grid codes. Okay, and but there's much recent interest in this topic because of two, I would say, because of two ideas. First of all, the discovery of circumbinary planets, of course. Yeah, this gave rise to new studies on the subject here to understand how they get there, can they form there, in this vicinity, close vicinity of the binary star, and how is the dynamical evolution. And then the evolution of the binary orbit itself. There is a quite intense recent discussion whether the binary will actually expand or shrink. Usually it was assumed it will shrink because the binary, which is symbolized here by the stars, as I said, transfers angular momentum to the disk and loses angular momentum and hence shrinks. Okay, and but recent studies seem to indicate, well, if the binary accretes also angular momentum, maybe the story is a little bit different. I will not go into the second topic here. We are working actually now very intensively together with Anna Penslin, my PhD student here, on the second topic. But today I would like to just, talk about the first topic here, the circumbinary topic. Okay. I assume that you will ask also questions in between. I mean, that's how we do it here. This is always very informal, our seminars here, but I leave it entirely up to you whether you want to interrupt here, even though it's not an interruption, I may say, or whether you would like to keep the questions until the end of the talk. Okay, this is just certain, let's say, applications that one can, where one has the action of circumbinary disks with a binary star here. This is an observation sometime 10 years ago here, Mayama and others here, this stellar system SR22, and they also did some numerical simulations here, which roughly, as you can see, resemble the observed structure rather well, but the focus is here not so much on the circumbinary disk, but rather on the two circumstellar disks that are also forming, of course, around the individual stars. A long time ago, a student, my first, as I said, diploma student, Richard Günther, did some simulations here. I hope they can play. So here you can see the dynamics of such a disk as they show here in the diagram here. This is from his diploma thesis. This is for a DQ tau star, but it doesn't really matter. So that's an eccentric binary star in the center, and you can see that there's lots of interesting dynamics going on. Okay, and this was done with a special type of grid or numerical method. This is a grid method which has a cylindrical grid combined with a Cartesian grid in the center, so we could cover the whole dynamics here. As you can see, there's a mass exchange between the binaries, and then there's some streams going back here, but there's lots of, let's say, what should I say, numerical stuff still going on here. Okay, this was a study nearly 10 years ago now by Richard Günther, and then the other topic of interest is black hole binaries. I mentioned this briefly here. This is a work by Phil Armitage and Natarajan. And 20 years ago, also, they looked at the evolution of the binary elements here, and they had a disk around a binary, two binary black holes. That's why one cannot see them here in the center. And there's a disk around it, and then they looked at the angular momentum transfer from the binary to the disk, and they saw a shrinkage of the orbit. And initially, it's hydrodynamical shrinkage here, and then when gravitational wave sets in, then they shrink even faster here, and then they merge. And as we know, after that, some 13 years later, they have been discovered, these through LIGO, the merging of black holes. So it plays a role in protostars, young stars, and also in the early phase of the universe with black hole mergers. All right. So after this introduction, if there's no questions from your side, I will continue with circumbinary planets and tell you a little bit about the discovery there, but this is just a very brief summary of their properties. Okay, I would like to introduce here the notion of P-type and S-type orbits. I mean, for those of you who are doing simulations, n-body simulations or something similar, the systems we are talking about now belong to the upper systems. Here you have in the center, you have a binary star here, and surrounding the two stars is something in orbit here, a debris disk, which could be the remnant of planet formation here. And this we call a p-type orbit because the particles that orbit the two stars this orbit is very similar to the orbit around a single star that a planet would have. And then, interesting enough, for binaries which have a medium separation, there's no disks observed surrounding them, and for large binary separations, you have then the situation that you have a disk around one star here, and then the other star acts as a perturber far out. So our situation is the first one here. So, and the stars indeed that we are talking about, and where then later, so this is 2007, this paper, when later have been planets discovered through the Kepler Space Telescope, these were always systems where the stars were really very close together. Okay, so I mentioned here Kepler 16, which is arguably the most famous of all systems. Here it has been discovered 2011, so it's 10 years ago. Amazing, seems to be like yesterday. And interesting here is that, I mean, you have three objects here, two stars and one planet orbiting the two stars. And all these three objects throw mutual eclipses of each other. So there's all in one plane. So the planet orbits the binary in the same plane as the orbital plane of the binary here. And that's why if you look at the light curve of the Kepler 16 system here, which is at the top here, you can see by this colored arrows, different type of eclipses. And so for example, the blue one here is when star B eclipses A, then you have star A eclipses B, and planet B, planet lowercase b eclipses star A, and planet B eclipses star B. So this gives rise to different types of eclipses, and they come in a sort of semi-regular basis, depending on the eccentricity of the binary, of course, and the eccentricity of the planetary orbit. And as you can see also, since both of these systems can have different eccentricities, it's not so easy to disentangle the complete dynamics of such a system there. Okay, so you needed to make a dynamical model, of course, to get it all right. But nevertheless, today about a dozen systems have been discovered. After these discoveries, of course, the question arises, well, under what conditions are such orbits of circumbinary planets stable? It's clear that the binary's potential being disturbed by the binary. It's not a Newtonian potential, I mean, so it has higher multipole moments, and this gives rise to perturbations to the orbit of the planet, and clearly it will affect the stability here. And there's classic work by Holman Wiegert and by Rudi Dvorak in the 1990s and even earlier that study the stability here, and they derive a critical semi-major axis AC here, and if the semi-major axis of the planet lies below here in this region, the orbit would be unstable because the planet is too close to the binary star. However, if the planet is above the curve here, for example, then the orbit would be stable. So this is the critical semi-major axis, only beyond which the orbits are stable, and this depends, of course, on the binary eccentricity. This is very clear. Okay, they give a functional relation here by this formula 1 here, and so stable orbits only if the planet orbits beyond this. Okay, but in addition, there's resonances. I do not go into this here. And at the resonant locations, for example, 4-to-1, 5-to-1, and those resonances with the binary orbit, the planets are all unstable. Okay, so resonances are really unstable. Good. And now the parameters we have for the binaries here. I just summarize them here. So we have very compact binary stars. As you can see, a fraction of an AU, even inside Mercury's orbit, all of them. And but the binary eccentricity varies a lot from nearly circular to highly eccentric. The planetary parameters, the most important here is indeed the red line here, which shows that the planets are very close to the stability limit, which I've just calculated, or Holman Wiegand have calculated, and just very close to the limit here, and then 1.5, 1.6 times that limit here. And the eccentricities are modest, yes, because if the eccentricities were larger, these planetary orbits would be unstable typically, as we have seen also. Good. That's the summary of the parameters here. I will go in more detail when we discuss individual stars, where they differ and what the impact of those parameters are. First on the disk dynamics, and then secondly on the dynamics of embedded planets in the disk. Okay, and about 12 systems are known today. I don't know if there's something new has been added or not recently. Yes. Okay, this is another diagram illustrating the same thing after all. So there's the two binary stars here, and they are separated here, and a rough rule of thumb here is that the planets must be beyond 3 binary separations, binary semi-major axes. Otherwise, they would be unstable here. Okay, and this is some famous systems here. Okay, good. I hope everything is still fine. You can still hear me. So the question is now, what brings those planets so close to the star, so close to the instability limit? So this is, of course, closely related to the Star Wars series here, where we have here the binary star, I think Tatooine, yeah, Tatooine, I think is the planet, and the binary star, this planet orbits this binary star. I can't see my pointer anymore, but maybe it disappears. Okay, good. So we assume here for this talk that the planets have formed further out and then moved to their current location. And the reason for that is that studies have shown that in situ formation of planets at those close distances of the binary star are essentially impossible. Okay, there have been several studies there looking at the dynamics of particles, planetesimals, and so on. And this is in a very tricky business to form planets there. So we just assume they have formed further out and they moved inwards. Okay. Let's talk about the disk dynamics before we add the planets. Okay. So we do numerical modelings here, and we are doing two-dimensional simulations. So since we have seen that the planets orbit the disk in the same, the binary in the same plane, so we can assume that they all were formed in one plane here. So we do two-dimensional hydrodynamical simulations, grid-based, and also now recently SPH in our group here. And we do here, can you see my cursor?
No.
No, I cannot see it myself. Let me see. It's 1 second only. I will be coming back. This is only a test whether you can still hear me. So let me go on here. Just now we have it again. So we do viscous dynamics here. Yes, thank you. Where we have the alpha viscosity. I think you hopefully know all this. And we have the sound speed here and the scale height. So the viscosity is parameterized through this constant value of alpha. No self-gravity, locally isothermal, these are just parameters. We did also radiative disks in one of our recent papers. And typically we have a cylindrical grid centered on the barycenter of the binary star. So which is depicted here on the left-hand side. We have the cross is the center of mass of the binary here. The binary star in yellow, and then you have the inner disk radius R min and the outer disk radius R max here. And important for our studies here, the R min must be at least, or the maximum R min that you should take is A bin, okay, the semi-major axis of the binary. This way we have shown this in a study a few years ago, and because recently it was taken sometimes a little bit bigger, and this is not very useful. All right, I will not go into numerical issues here. You can ask me later on. It's a little bit tricky to do this, and so it took us some time to get the right setup and convincing results here. To validate our results, we use different codes, Fargo, Pluto, and recently also more SPH code as well. Okay. This is our study. So this dynamic sample systems, yes, sample systems here, there's a table, but with very few entries. I just want to point out two things here. The systems in red, K34, Kepler 34 and Kepler 413, have planets with relatively high eccentricities here. Okay, that's on the right color here. But the binary eccentricity for Kepler 34 is very large, but for Kepler 413 is very small. Okay, just keep this in mind. And then we'll look later on, I will have several models for Kepler 38, which is a sort of standard case for our purposes here, with a moderate mass ratio Q-bin here and moderate eccentricity of the binary and relatively small eccentricity of the planet. Okay, there's just smaller 0.03, but this is just a limit here. It's probably bigger. Also, the eccentricity of Kepler 16 here is a little bit underestimated, because if we average it, it's typically a little bit higher. Okay, so these are some parameters of the systems here. And then we do some simulations. How do they look like? If you switch it on, the system here, then the binary, if you just start it up, the binary will open the disk here. So we'll immediately create, not even after one orbit, essentially, begin to clear out the gap here. And in very few days, as you can see here, through spiral arms can transfer angular momentum from the binary to the disk. Then we speed up the simulation here, and you can see after a few orbits here, you begin to open up a very nice and decent gap, or cavity. We call it cavity here. And there's still a lot of interesting dynamics here. If you would like to model the system like this, where you cover also the central parts here, then this simulation would take forever. So we need to cut out the inner region and just model the outer disk structure, which is justified, because if you have a well-defined gap, these two evolutions are somewhat separated from each other, and you can capture the dynamics even though you have a hole here, like here in this case. So here the white region inside, this is the inner hole of the disk, and you can see for that simulation here, this is Kepler 38, the disk is well separated from the inner region here, and you can model it even without covering the central parts here. So we have here, as you can see, a precessing disk around the binary planet, and which is then slowly orbiting, slowly precessing here, and the disk is eccentric. So that's the typical structure here. So I've summarized this also already here. So the disks show very spiky densities here. They have a large eccentric hole, and they show a coherent precession with a slow precession rate. Here's also, I think, I have quite a few animations because I think it's so nice. This is now a very eccentric disk, okay? And here you can see with the red arrow here, you can see the precession of the disk, and the green arrow is the periapse of the binary star. Can you still see the movie running?
Yes, you can. Yes.
Okay, because on my additional screen, it's very, very rough. Okay, so I hope you can see it moving a little bit. Thank you very much for the feedback. Okay, so you can see here the binary parameters do not change here, and this was a live binary here, and the disk precesses around this. Okay, this was Kepler 34, very eccentric disk, Kepler 38. Relatively mildly eccentric disk. I will come to the details then. So here is the summary here. This is results for given mass ratio of the binary star here. And then we took different binary eccentricities here. So this is a low binary eccentricity, then it increases 0.2, 0.3, 0.56, and this is Kepler 42 here, Kepler 54, I think here, which with a very high eccentricity here, and you can see the eccentricity of the cavity changes with the eccentricity of the binary, and also the precession rate here changes with the eccentricity of the binary here. Okay, that's our main finding, and we found that all disks, no matter whether the binary is circular or eccentric, all of these disks become eccentric. That's the most important message. And here we plot for many different parameters, for different binary mass ratios Q, we plot the precession rate on the y-axis here, and the cavity size, the resulting cavity size on the x-axis here. Okay, and you can see the numbers here on this the labels here, they quote the binary eccentricity, and the colors give the binary's mass ratio. And you can see if you scale the precession rate on the y-axis by the precession rate that a single test particle orbiting the binary would have, which is given by this analytical formula, then all the models lie on one curve here, which shows a little bifurcation here at medium binary eccentricities. The disks are most circular, okay? And the disks or the cavity is smallest. For medium binary eccentricity, the cavity is smallest and the cavity size increases for very low binary eccentricities here and for very high binary eccentricities here, okay? This is a little surprise, or was a little surprise when we saw it, okay? We called this bifurcation diagram. But it's also very illustrative to look at this in a different diagram here, where we plot the resulting gaps. We used to call it gap, but we call it cavity now. So the binary opens the inner cavity, and we reserve the name gap for an embedded planet and the planetary gap. So if you have low binary eccentricities, the red circle here, so this is 0.04 binary eccentricity, then the eccentricity of the resulting cavity is largest. So circular binaries create the most eccentric cavities, okay? Then if you increase the binary eccentricity, you move down here, down to this low end here, where the gap become least eccentric and smallest, okay? And then if you go up again here, you move up here to this high eccentric region here with Kepler 34, which has an eccentricity, binary eccentricity of 0.52, which show the largest cavity sizes here, okay? This is quite an interesting diagram here. And we remember now that the planets for which we have the largest eccentricities was exactly Kepler 34, which is here, and Kepler 413, which is here, okay? So those extreme cases here showed the largest planetary eccentricities, and the other planets were all in this region down here. Okay, that's the structure of the cavity, a little surprising result here as well. Now we come to planets in the fourth part of this talk.
May I just make a question?
Yes, please.
How does that depend on, for instance, the viscosity of the disk? Does it change significantly or keeps this kind of?
I will come to that. You can.
Okay.
I'll wait. Yes, I will mention a little bit. That's a very good question. I will mention a little bit about the viscosity in a moment. Yes. Okay. Of course, this was a standard viscosity. I think 10⁻² or 10⁻³ we took here for alpha. but we have no more models. I will come to that. Okay, now we embed planets into the disk. All right, and the question is, what does the planet do? And for this, we take, I think, Kepler 38 as a reference system here, which had a relatively low binary eccentricity, 0.1-ish, and a mass ratio of 0.3 or something. Okay, we embed two planets here in this in these disks here, and you can see the evolution of the eccentricity of the disk here, and the corresponding precession rate here at the bottom. And the planet is inserted after 10,000 orbits. So here, at that point, we insert the planet, and you can see the planet makes the disk eccentricity drop quite substantially. The massive planet of 0.38 Jupiter masses here, which is the observed maximum mass of the planet in Kepler 38, by the way, makes the disk eccentricity drop, while a planet of lower mass on the right makes the eccentricity of the disk drop a little bit only. Okay, and at the same time, we can see here, if you look at the pericenter here, we can see here that you still have a very nice precession of the disk here in that case. And here the disk is too circular, so yeah, there's relatively ill-defined precession rate here, if anything at all. Okay, so that's how we do it. We bring the disk first in equilibrium, 10,000 orbits, and then we embed the planet. Okay, and then where's the planet parked in these simulations here? The planet is always parked near the inner edge here. You can see this here on the left side. These are surface density distributions plotted at different times. And the planet is the dot here. So the planets are parked at this positive density slope in the center, which is a known effect that is a zero torque condition for the planet. So it doesn't go in, doesn't go out. Okay. And for the high mass planet, the disk becomes more circular, the planet moves further in, and the planet is on a circular orbit. Okay. For the lower mass planet here, the disk remains more eccentric, as we have seen, and the planet stops further out, and the planet orbit remains eccentric, and the orbit of the planet and the disk show apsidal alignment. Okay, I will demonstrate this in the following. Okay, and this depends here only on the mass of the planet. We'll come to this later. This final parking position is unique. I'll just point this out. If we start the planet here at different initial positions, 10, 6, and 3 binary separations here, they all end up at the same location on the right. So even if you start inside of the disk cavity, the planet moves out like the green curve and goes to its desired position there. Okay, good. So this is fine. That for given disk parameters, so viscosity and things are given, we find a unique planet location for these different models, which is promising. Okay, what determines the final position of the planet? Okay, and this is shown here for different simulations with 2 different disk masses and 2 different viscosities. And to summarize, what you see is that for the 2 high viscosity models, blue and orange, the planet remains further out and on an eccentric orbit. Okay, and the reason for this is the gap opening ability of the planet. Okay, the criterion whether a planet remains eccentric or becomes circular or moves further in depends whether the planet opens a gap or not, which depends first on the mass of the planet. Given the viscosity, it depends on the mass. And if you give the mass, then it depends on the viscosity. So lower viscosity will allow for a gap of the planet to be opened. So which is a gap of the planet versus cavity of the disk. So gap opened means the planet splits the disk into 2 sections. The impact of the binary is reduced in the outer disk. The outer disk becomes more circular. The planet moves further in. Okay, there's a little misprint, I think. Here. Okay, Yes, that's the action here. You have a separation of the disk, so the waves emanating from the binary into the disk cannot propagate completely through the disk because of the presence of the planet, which has opened a gap. All right, and this gives rise to much different evolutions here. Here's, by the way, the observed location here, so we can see already if the disk is too viscous and the planet does not open up a gap, the planets would end up here and would not be able to move down here. Okay, so you need to have low viscosities in the disk to get down there. All right. And here's the two states again. So for the high viscosity where the planet remained further away, the disk stayed eccentric and the planet orbit is also eccentric. And these two orbits are fully aligned. As you can see here, this is the pericenter or longitude of pericenter of the planet in blue and the disk in red, and they are fully aligned over whatever, a few thousand orbits here, as long, but forever after all. Okay, and here on the right-hand side, you see the low state for low viscosity here. The disk and planets are very circular here, and there's no alignment visible in this sense. Okay. I will come to the viscosity. Now we study 10 Kepler systems. This is our most recent work here by my student Anna Penslin, myself, and together with Richard Nelson. We have talked about him when he was a young student in London at the time. So when I was a postdoc there, and Oton was also there in London, he was a young student, and now he's a professor there. So this is how life evolves. Okay, Richard Nelson joined our team here, and we did some work on this. And he also did work previously with Arno Pierens on these problems here. So these are our systems that we studied here. There's now, the number has increased. The first papers we have done were there was only a handful of systems. Now we have a dozen, and 10 we analyzed here. So here we have the most eccentric systems. I managed this already here. The planets here, the planets are very eccentric here, and here the semi-major axis and so on. Okay, now we try to find disk parameters that allow embedded planets with the observed mass to park at the right position. And we have seen already we need to play around with the disk viscosity, for example, all right? And we can play around with the disk thickness, with the temperature in the disk, okay? And this is now coming to answer the question which was raised here. Okay, now we study disks with different viscosities, but otherwise similar parameters here. And here you can see for Kepler 35 parameters with viscosity alpha 10⁻², alpha 10⁻³, and alpha 10⁻⁴. Okay, you can see here the states of the disk after the disk has evolved for 25,000 binary orbits without a planet. And this we call T0 because then we add the planet. So we first have the disk evolution for 25,000 binary orbits. And this already takes quite a bit of computer time, I'll let you know. And then we add the planet to this. And we can see here the different structure. That was the question. If we have very low viscosity here, the disk are very circular, very low eccentricity. And the cavity size here is relatively small. If we take the viscosity higher, we can see the eccentricity of the cavity rises, and then also the cavity size is a little bit bigger. Despite the larger viscosity, because everybody would have thought, well, if the viscosity is higher, the disk tends to shrink here and move further in. But the binary action of the disk plays also, the gravitational action of the binary plays also a big role. And for the value of the viscosity, well, I mean, nowadays people believe, in fact, that 10⁻⁴-ish is the value that is operating, at which these disks are operating, okay? Not the very high values here. So this is not unreasonable here, okay? Now, and in blue, you see now here the planet when we just embed it into these disk structures here. And this is the orbit where we embed the planets. I think this is 6 A-bin or something here, okay? And then we get this evolution here, okay? So we can see here now the 3 cases here, and where we add the planet into these disks with the different viscosities here, all right? And you can see that on the left side, when we have the large viscosity here, the disks essentially remain eccentric, and the planetary orbit is also eccentric here. And when we move to the right here, the planetary orbit becomes less and less eccentric and also more compact. Okay, so this changes the same time it changes the planet semi-major axis and the planetary eccentricity. All right. Good. Then we move ahead, and here you can see the summary, what I just said. This is after 30,000 additional binary orbits here. You can see here's the parameters of the planet that we found for these different viscosities here. And I think we took a disk thickness here of h/r 0.04, I think. Okay. And then we study the 10 systems here, 8 of which are displayed here. So we have here, we do this for all these game here that I just explained to you. We do for all these systems here. So there was hours of computer time burnt or something, as you would say. Not very good for the climate, but anyhow, okay, but good for astrophysics. And that's important here. And so you can see h is the scale height here, the thickness of the disk. Alpha value is given here. So typically alpha is 10 to minus 4. And for Kepler 38, which I've mentioned before, we have a little bit higher alpha also and higher h/r, because the planet is more massive in that case. So we don't need to go so low in viscosity and the disk thickness here. All right. So the mass of the planet, of course, plays also a role on its ability to open a gap or not a gap. All right. And we can see here that here the disk is still relatively eccentric here, but in the other cases, the disk is already quite circular. So if you embed a planet into such disk, we will expect also a circular orbit here, which we observe. So this is for the binary eccentricity 0.05 to 0.25. But if we have the most eccentric binary, Kepler 34, then the disk remains very eccentric despite the low viscosity and the low scale height. And for very small binary eccentricities, in those cases here, the disks also are more eccentric, and which is then more difficult for the planets to come close to the stars. So these are in green, the systems up there, and in red and white, the other systems below. And as we shall see, the green planets, we could match them successfully and the other ones not. Okay, this is now when we do these simulations here, 10 systems we have, and I show you now the successful evolution, 6 out of 10. This is our recent paper with Anna. 6 out of 10 planets reach the observed state, essentially. So this is plotted here. On the left, we see on the top, we see the semi-major axis evolution of these 6 cases here. And in the bottom panel, we see the corresponding eccentricity evolution of the planet for these 6 cases here, okay? And this gray shaded region here is a 10% deviation from the observed distance of the planet from the binary star. We can see that all of these reach essentially here, this limit here. So this is after 70,000 binary orbits, and the green model here, Kepler 38, I think has been continued further, and it reaches also this gray region after 100,000 or so orbits, I think. Okay, and here in the bottom part, the eccentricity of all these systems is also relatively low, but here we see the deviation from the observed one, so everything is between 0.05, I think, of the observed eccentricities here, and sometimes we see that there's an eccentricity rise here in between these evolutions here, and we attribute those to temporary capture in a resonance with the binary star. Okay, and here we show again the viscosity here. We have low viscosities for these cases here, usually 10 minus 4, not for Kepler 38, and h/r is 0.04. So relatively thin disk with low viscosities, but this is not unreasonable as studies show, recent studies show. And so from our simulations here, if we believe that planets, circumbinary planets, have formed this way, these simulations can also give some indication on the physical state of the disk at the time of formation, so which is otherwise, of course, very difficult to get to. And the unsuccessful evolutions, 4 out of 10, so at least we have the majority of successful simulations here. These are the ones where the binaries have low or high binary eccentricity. So here I think latex was something still wrong. We have low or high binary eccentricity here. They show not an agreement here, and we are still working on this. So we are working on they still have small viscosity, small h/r here, but some physics may be missing on those models here, or the evolution is different here. So this is binary stars which would have very eccentric disks when they were still surrounded by circumbinary disks, and for those stars it is difficult to get the planets to the observed locations here. So maybe there's an additional planet, there's 2 planets. In fact, Kepler 47 here, the red one, has more than 1 planet in it. So whether this makes a difference or not is not clear. Yes, or whether the disks, we need to have 3D effects for those disks or whatever. Okay, this is not known at the current time. All right, and here we compare our results for the 10 systems here. And here we have the observed eccentricity here. And here we have the observed semi-major axis here. And you can see here the observed location. I think this should be here. Yes, the parameters of the planet. So we can see in the solid circles are the observations, and the shaded circles are the simulations here. You can see for the disks which are more eccentric, the agreement is not that good, but for the disks which are more circular, the agreement is very good here. Down here, there are successful systems, and the others deviate quite a bit. And successful means, as I said, 10% agreement in the semi-major axis here. Okay, our result from here is typically that we need relatively small disk viscosity to get them at the right positions. Okay, this is my second to last slide here. There's some more animations in the end, okay? And on the left, we have a little animation from an old paper of myself and Nader Hagegipur, where we show the short-term evolution here. So here is the binary here, this Kepler 34 binary, eccentric binary here. You see how it moves, and there's the spiral arms here emanating from the binary here, and the planet is moving around the binary here on its orbit here, and the planetary and binary orbit are, I think in this case, also fully aligned. I don't have now here the alignment shown, but this is how it looks like, okay, for Kepler 34. But the planet stops here too far out, okay? And here is the other systems, and which also shows the evolution here. These are all the systems here where the planets stop too far out. So these are the unsuccessful systems here that I show here. But these animations look quite nice. You can see that the orbits of the planet here and the disk in this left case is really nicely aligned. You see the planet and the disk's ellipses here are very nicely aligned here on the right-hand side here, and also here on the left side, and also on the right side. I think in the middle is a little bit more tricky here. Okay, so and these are the parameters here of the planets here, planet parameters here. They surprisingly, for some reason, they have always 0.16 here. Okay, I should ask Anna whether this is all okay. But the semi-major axis changes slightly here. Okay. So this is the dynamical evolution of these cases, which were eventually unsuccessful still. Okay, and this comes to the end of the talk here. I hope I didn't keep you too long here. So we have first discussed the disk dynamics here, which is very complex, and it depends on the binary parameter first, binary eccentricity, and the binary mass ratio does not play such a big role, actually. You can, by suitable scaling, you can put them on top of each other. So the main influence is binary eccentricity. We have an eccentric hole in the center of the disk for all binary parameters, also for the circular binary parameters. And there's this bifurcation diagram, as we have seen, and the largest cavity sizes are for the small and high binary eccentricity systems. Here, the planets move to the inner edge of the disk because there we have a planetary gap due to the very steep positive surface density gradient there. Then more massive planets can move further in because they open a gap in the disk. And in low viscosity disk, planets also move closer in because they open a gap in the disk here. Okay, and we obtain relatively good fits to the observations for systems with intermediate binary eccentricities. On the other systems, we still have to do some more work. Yeah, thank you very much. This was my very last slide. I hope you could hear me till the very end. And now
yes,
it's open to questions. Yes.
Yes, it was perfect. The sound and the image, the videos, everything worked perfect.
Okay, very good.
So now we can open for questions. Anybody would like to make a comment or make a question?
I have a question, Willie. Well, as the planet gets closer to the cavity, does it change the structure of the cavity?
Yes.
Like in
yes.
Okay.
Yes, it does. It does. I have it. I go back here. You see, here is the plot. You see, here we have here's the disk. So before 10,000, there's only the disk, and then we add the planet, and you can see that this is the disk parameters plotted here. So you can see the disk becomes more circular if the planet has more mass, and the disk remains more eccentric if the planet has lower mass. So the addition of the planet certainly changes the disk structure. Yes, and the
yes, but the cavity structure as well. I mean, the cavity of the two binaries of the binary.
Yeah, this. I mean, if I say here, sorry, if I say here the disk eccentricity, this is the cavity eccentricity after all.
Okay.
Yeah, sorry, this may have been a misunderstanding. Sorry. I mean, we measure the eccentricity of the cavity by fitting an ellipsis here, to the inner cavity. I think I had it here somewhere. Sorry, here we fit an ellipsis here, and in the, let's say, region a little bit outside of the cavity, which we call disk here, the whole region precesses rigidly. Okay, so this is a sort of global mode here. There's a region in the disk which precesses rigidly. So we usually say e-disk, but it's actually e-cavity. Yes, sorry. Okay. So that's what you can see here. And we just do an analysis of all the disks here and fit automatically this ellipsis to the inner region here. So we check where the boundary is, and then we fit an ellipse, approximate ellipse there. Yes. Good point.
Okay, so let's join into his question. So the ellipsis, the eccentricity, and the upside of precession, they are measured fitting one by one.
Yes, yes, it's automatically.
That was my point. Okay,
it's done automatically. We describe it in the paper with Daniel, I think, in our 2018 paper or so. We describe the method. And this can be done in principle on the fly while you are running the model. This can be done while the simulation is running. It's automatically.
Oh, I see.
Yes, well, we have designed a method to calculate this on the fly. Yeah, so we don't need to store all the models. So we do this automatically, yes. And sometimes, of course, if there's some noise, sometimes you can see this if you look carefully in the evolutions here. Where is it? Sorry for this. Here you can see sometimes there's some wiggling and so on. But in principle, this works relatively nicely. Yes.
Okay, good.
It was a bit tricky. We explain it in our paper relatively exactly how we do it. But it was, of course, a little bit tricky to figure it out exactly how to do it.
Okay, okay, good. Anybody else? Another question?
I have one too in reality.
Please.
Really nice talk. Regarding this figure that you are showing here, why do the precision rates change for the lower example?
For these cases here? Yes.
Yes.
If you have a disk, or let's say a binary, which is more eccentric, so this is an eccentric binary with a 0.56, we observe that the disk shows a slower precession rate. Okay, this is a finding we have. And if you go to this diagram here, this is the precession rate here. You can see that disks where the binary is more eccentric here have a larger cavity size. Okay, they have very large cavity. And it's, I think, understandable that larger cavities must, in a sense, precess slower, because the dynamical times, they are also longer here. But don't forget here, the precession rates, if you look at this diagram here, they are thousands of orbits. You see that the disks show very, very slow precession rate. Okay.
Yes, but in the bottom frame of your previous figure, you have a precession of the disk that it changes with the time.
Here you mean?
Yes.
On the right. Yes, yeah. Yeah, sorry. We only show the initial phase. You have to wait long enough here, and then it becomes constant. So we measure the precession rates which I display here are measured after 20,000 binary orbits. So we wait. Very good question. We wait until these disks become into equilibrium, and then we measure. Then we plot those precession rates. Initially, of course, here when we start up here, the top one here, for example, very, very fast precession, because the binary hole is still very small, and then it slowly increases here. And then we wait, as I say, 10, 20,000 orbits until this is in equilibrium, yes. Yeah, and this is important, because otherwise you would get the wrong results. And in fact, many simulations you see in the literature, just to point this out to you guys, have only done 2,000 orbits. This is not enough. Yes, you need more, much more.
How long it takes each iteration?
10, 20,000 orbits. It depends. If you have very low
CPU time in computer time. Days,
uncountable. No, we do this here, which I said here, if you're interested. We do this with a GPU-based code, which has been written by Daniel Thun, which is based on Pluto, on the Pluto Riemann solver code, and which is now used by Anna, and she improves it also. So we use this GPU code here, and we can run it on 2 to 4 GPUs. And for one model, I think, depending what the viscosity is, we would need a few weeks. Yes,
okay.
For one.
Thanks.
On this GPU. Yeah.
Okay. Thanks.
On a regular CPU-based code, we would take a little bit longer. Yes, I mean, then we would run it typically on 28 cores, let's say, 28 to 54 cores, 56 cores, and then we would have a similar time. Yes, so one GPU is something like 30 CPU cores. Yeah.
Okay.
Okay. Yeah.
Any other question? Any more comments or questions? Well, I have one about the resonance. Yep. You showed some temporary capture. Is there any possibility? Did you find any kind of more permanent or longer time duration capture?
Not in these simulations here. The point is that the planet migration may be too fast, so it just crosses the resonance. To be captured in the resonances, as you might know, you would need relatively low or slow migration speed.
Slow migration, yeah.
Yes, then you will have enough time to be captured in the resonance here. And here, if you see the initial phases here, it's very fast, but then later on here, there's some phase here where they captured temporarily. We did not, for these simulations, we did not analyze actually whether there is a temporary capture in the resonance. In a previous paper, we did this, and we found capture in sometimes also in higher order resonances here. Yes, and but in these cases we haven't analyzed this. But this is our suspicion here, that when the eccentricity gets high, you temporarily are captured in this resonance. We might analyze this, yes. And then it's the damping action of the disk that keeps them stable, yes. I mean, if you just certain resonances, as you also know, are unstable if there's no disk. But if you have the damping action of the disk, in addition, then it can remain stable. The planet can remain stable and cross it. Yes, safely. But the final orbits are not in resonance here.
Okay, okay. Good.
Yeah.
So, any other comment or question, please?
And I think if I may just comment here on the final diagram here, the final orbits are somehow, I believe, so between the 4-to-1 and 5-to-1, or 5-to-1 and 6-to-1 resonances with the binary. So that's the planets are lying in between those resonances there, so they are on stable islands, let's say. Okay, yeah, sorry.
Okay, good, good. So any further question or comments? Okay, so thank you very much for the presentation. It was great. I think it is very interesting work and new results. So thanks very much.
Yeah, thank you for listening. Thank you for the invitation, of course.
Okay, let's hope we have the opportunity to have you here in Brazil and meet personally. Okay.
Yeah. There were so many people here, but I was never there. Yes, that's true.
Okay, we'll find an opportunity.
Yeah, yeah. Okay.
Okay.
Thank you very much. Yes.
Okay. So thanks very much. Okay, good.
Thank you.
So just before finishing our meeting, we just have a time for